All right, guys, so let's go ahead and look at today's lesson. We're going to be beginning our unit on trigonometric functions. So we're going to start with just a lot of vocab here, talking about angles and their measures and some of their characteristics. And so this may feel a little bit like a geometry lesson, but this is going to be necessary vocab to kind of lay the foundation for what we're going to be doing with trigonometry and those trigonometric functions in a little bit here. So anyway, beginning with angle characteristics. So a couple of just vocab review terms here. So an angle is determined by rotating a ray about its endpoint. And so we have some special names there. So the vertex is the endpoint of the ray. The initial side is the starting position. And the terminal side is the position after rotation. And so standard position angles, angles that are in standard position are placed on a coordinate plane with the vertex at the origin and the initial side on the positive x-axis. So you can see the picture there. And so kind of the normal way that we think of measuring angles is to go in the counterclockwise direction. And so when we do that, we get positive angle measures. So looking at this particular example that's drawn in there, we can see that the arrow is going in the counterclockwise direction. And so this is going to be an angle a little bit more than 90 degrees. We could call it, I don't know, 110 degrees or something like that. So that's going to be a positive angle measure. Versus if we go in the counterclockwise direction, we would get a negative angle. So for example, if we were looking at the exact same angle here, but going in the counterclockwise direction, that would take us in this direction here, and we would get a negative angle. And so just a reminder, there's 360 degrees in a circle. So to figure out what that negative angle would be, I would be subtracting the 110 degrees from that, which is going to give me 250 degrees, but it's going to be negative because I went in the clockwise direction. So this would be a negative 250 degree angle. Coterminal angles are two angles that are in standard position that share the same terminal side. So because they're in standard position, that means that they both are starting with their initial side on the x-axis. So essentially, these are angles that are going to look exactly the same in terms of their two sides. The only difference is that they are going to be measured differently by either adding or subtracting an entire revolution. And so let's go ahead and do an example here. So if I draw the angle theta equals 220 degrees, that's going to look like this angle right here. So I would draw in standard position. I'm going to go ahead and put my, let's try this again here. Go ahead and put my vertex here on the x-axis, draw my initial side, and then 220 degrees is going to be right over about here. And so if I go ahead and draw that, it's a positive angle, so I know I need to go in the counterclockwise direction. So theta would be this angle right here, which we said was 220 degrees. So a coterminal angle is going to be one that shares that same terminal side, also in standard position. And so if I were to take, kind of the same idea here, I've got my initial side, I've got my terminal side, but I have a couple of options here. I could go kind of in the same counterclockwise direction and do an extra revolution. So I could kind of go around. I don't know why it keeps erasing it for me here. Let's try that again. So I could go here and go around, and then go around a second time and end up in the same place. So that right there would give me one coterminal angle. So I'm going to call that theta prime. And so that would just be still going to be positive. I'm going in the counterclockwise direction, but I'm going to add 360 to it. So I'd be doing the original 220 and adding 360 to it, which would give me an angle of 580 degrees. So that would be one angle that is coterminal. Another one would be by maybe subtracting 360 from the 220, or in other words, kind of going in the in the clockwise direction. So if I were to draw in that angle there, draw in again the same ending point here, but instead of going 220 in the positive direction, I actually subtract 360, which has me going in the negative direction. And so I'm going to call that angle theta double prime. And so I don't know why it's advancing here, but that angle then would be 220 minus 360, which would give me negative 140. Anyway, moving on here to reference angles. So given an angle in standard position, its reference angle is the acute angle formed by the terminal side of the given angle and the x-axis. So in our picture here, we've got our angle that looks like it would be 210 degrees is what they told us here. And so the reference angle would be the acute angle between that terminal side and the x-axis. So it would be this angle right here. And so if I know that, all the way to the x-axis is going to be 180 degrees. So if my total angle is 210 degrees and I subtract the 180 for kind of that straight line, that lets me know that that smaller acute angle that I'm drawing is 30 degrees. And so that would be considered the reference angle. 30 degrees. All right, so a couple of examples here. You'll have some of these in your homework where I ask you to draw each angle and state the reference angle. So the first thing I'm going to do is kind of estimate roughly what the original angle would be. And so 150 degrees, I'm going to go ahead and draw in. It's going to be less than 180, more than that 90 degrees, so maybe about right there. I'm going to go ahead and label that as the kind of original angle of 150 degrees. And then I'm asked to go ahead and figure out what the reference angle would be. So my reference angle is going to be this guy right here. And so I know that it's got to be a total of 180 there. So if I have 150, I would need 30 more degrees for that angle there. And so I could go ahead and state that my reference angle is 30 degrees. So another example here, 315. So if I were going to estimate what that angle would look like, so 315 degrees, that's going to be getting close to that 360 degree. So I'm going to say it's about right here, and it would be this big angle right there. And so that would be the original angle, 315 degrees. The reference angle then would be the smaller one right here between that terminal side and the x-axis. So I could go ahead and draw that in, and it would be 45 degrees. And so I could go ahead and state that my reference angle is 45 degrees. All right, let's just do one more here. Letter C. So we've got negative 120 as kind of the original one. So remember, the negative tells me that I'm going to be going in the clockwise direction, so the opposite way that we normally go. So 120 degrees, that's going to be past that 90 degree, not quite 180. So we're going to call this the angle negative 120 degrees. And so then the reference angle is going to be this guy right here. And so that's going to be whatever I would need to complete the 180 right there, which is going to be another 60 degrees. All right, and part D is pretty much the same thing. So let's keep going here. This next part about degrees, minutes, and seconds, we're not going to focus a whole lot on it. You're welcome to kind of look at that here if you want, but it's just a way to kind of express not complete angles, so kind of like you have decimal points with normal numbers. We're not going to focus a lot on that. So let's keep going here. Here's a big topic that we want to talk about a little bit more. So we're going to talk about radians. It's another way for measuring angles. And so this kind of came from the late 1800s, where mathematicians began to see a need for another unit of a measure because they needed the angle measurements to cancel out. And we're going to see this is going to come to our to help a lot over the next several units here. But a couple of things about radians. Radians have no units, so there's not like a unit sign that goes on it like, inches. We use the double kind of the quotation mark. For degrees, we have the little degree symbol. Radians, there's no symbol. You would just say radians. And so one complete circular revolution in radians is 2 pi. So 2 pi radians. And so that's equivalent to 360 degrees. So when we talk about a full revolution in degrees, this full circular revolution in degrees is 360 degrees. In radians, though, it's 2 pi radians. And so, not super important here, but 1 radian is approximately 57.296 degrees. And so this idea of the radian is based on the concept of the unit circle. And so we're going to spend a lot of time talking about this year. And so a unit circle is just a circle whose radius is 1 unit with its center at the origin of the coordinate system. And so the radian measure of an angle is based on the length of the arc of the unit circle. And so we're going to spend more time talking about lengths of arcs and things like that later on, but here's just kind of your first introduction to the unit circle. All right, next vocab term here, central angles. And so we use a central angle of a unit circle, as you can see in the diagram here, where the vertex is at the center of the circle. And so 1 radian is the measure of the central angle that intercepts an arc equal in length to the radius of the circle. So the circumference of any circle, we know this formula, you should know this back from geometry. The circumference of a circle is 2 pi r, where r is the radius. So the circumference of the unit circle, if our r is 1, so if we think of this r value right here as being 1, then you can see that the radius, the circumference of that circle is going to end up being just 2 pi because we've replaced the r with 1. So therefore, an angle representing 1 complete revolution of the circle measures that 2 pi radians that we talked about a little bit ago. So with all of that kind of in mind, let's go ahead and just look at some common radian measures. So you guys probably know that some of the common degree measures of angles, we have 90-degree angles, 180-degree angles, ones that are kind of that you see showing up a lot or have significance to them. So let's talk about some of the common radian measures. And so here's just a few of them here. The first one is negative pi over 4 radians. And so keeping in mind that that 1 full revolution is going to be 2 pi. So if we know that the full revolution is going to be 2 pi, so we're thinking about, well, what would pi over 4 represent? So that's like 1/4 of 1 pi. And so if we're thinking of 2 pi as being the whole circle, 1/4 of a pi, there's going to be kind of 8 of those fourths within the 2 pi. So if we think of the whole circle being 2 pi, pi over 4, if we kind of were to divide that whole circle into fourths, or into pi over 4 sections, there would be 8 of those pi over 4 sections. And so if we were to draw that in here, that'd be kind of, let's see if I can get this to work here, look something like this. And so this first section here, negative going in the negative direction, that would be negative pi over 4. And so if you think about it, if you were to keep kind of going around here and adding them up, here would be another pi over 4, here would be another pi over 4, here's another pi over 4, and so on. So we kind of keep going around here. And if we were to count up all of those, they would total up to a total of 2 pi. So you'd have kind of 4 sections of pi's over 4 on the bottom, that would be like 1 pi, and 4 sections of pi over 4 on the top. Another helpful way to think about it here is if you're thinking that the whole circle, a full revolution is 2 pi, then a half revolution, half the unit circle from here to there is going to be pi, right? And so another way to think of it is if we're looking for pi over 4, that's going to be 1/4 of that half circle. Let's do another one here. So pi over 2 radians. So again, if you're thinking that, okay, the whole half of the circle is going to be pi, and I want to draw in pi over 2, so half of that, then I can begin to see, okay, well, pi over 2 radians is really going to be half of that half circle right here. So this is going to be a pi over 2 radians angle. And then the last one here is what we already kind of talked about. Half of the unit circle, or half rotation, is going to be pi. And so that's going to be actually just this, what we think of as like a 180-degree angle. This would be an angle of pi radians. So with these two different ways of measuring angles, you might be wondering, are we able to convert back and forth between the two? We can, so we kind of informally talked about it here in terms of thinking that a full circle is, 360 or 2 pi, but the simplest conversion formula for each here, converting from degrees to radians, what we're going to do is we're going to multiply by pi over 180 degrees. And then to go from radians to degrees, it's going to be the opposite here. We're going to multiply by 180 over pi. So we're going to multiply essentially by the reciprocal. And so if you see a couple of examples here, I think you'll understand why it makes sense that the formulas are what they are. And so example number 4 here, part A, we're given a measure 7 pi over 6. And so I can tell that that is radians because it does not have the degree symbol. And so I'm trying to go from radians to degrees. And so I'm going to use the second formula that I was given there. So I'm going to be multiplying by 180 over pi. So multiply by that. And so what you're going to see here is that that pi is going to cancel out. And so that's good because most of the time when we talk about degrees, we don't see that pi symbol. And so then I can go ahead and multiply those together here. And when I simplify here, I end up getting 210 degrees. So let's do an example kind of going the opposite direction here. So on this one, we're given in part D, we're given the measure in degrees. And so I'm trying to go 2 radians. So this time when I multiply, I'm going to multiply by the reciprocal pi over 180 degrees. And so when I do that this time, the pi is not going to cancel out, but what will cancel out is the degree symbol here. So we can kind of think of it as those degree symbols as canceling out, and that's good because I'm trying to get something in radians, which is not going to have degrees anymore. And so if I multiply that together, I'm going to leave things in terms of pi. So oftentimes with radians, things are written in terms of pi because radians are kind of defined by units of pi. So the full circle is 2 pi, half circle is pi. So we usually want our radians to be in terms of pi. So when I go ahead and multiply that together and do a little simplifying, it comes out to 3/4 pi as that angle measure in radians. So let's just do a couple more here. Part B, so here I am, I'm given it, there's no degree symbol, so I know that it is in radians. So I'm going to go ahead and multiply by 180 over pi. And so since I'm trying to go to degrees, I really do want those pi symbols to cancel out. And so when they do, and I do a little bit of simplifying here, I am going to get negative 120 degrees. And then we'll do one more here, E. So if I'm taking this negative 320 degrees, trying to convert it to radians, I'm going to multiply by pi over 180. And again, those degree symbols will cancel, just kind of like the pi symbols canceled for part B. And what I'm able to get here when I simplify is negative 16 over 9. And then I'm going to leave the pi in there. So a little bit more practice here, thinking about radians in some different contexts. So first question here is, how many radians is each angle of an equilateral triangle? So it might be helpful to review a little bit here what an equilateral triangle is. So if you remember, an equilateral triangle has equal sides and equal angles. And so if we know that all of the angles in a triangle have to add up to 180, then if we kind of divide them all evenly, we know that each angle is going to be 60 degrees. So oftentimes it's helpful to think about it in terms of degrees when we're talking about a geometric shape, but we want to know how many radians is each angle. So in other words, I'm trying to take that 60 degrees and convert it to radians. And so to do that, I'm going to multiply by my conversion factor here, which is the pi over 180 degrees. And again, the degree symbols kind of cancel then, and I'm able to simplify a little bit here when I'm multiplied together to get 1/3 pi, or sometimes you usually just see that written as pi over 3. So second question here, the minute hand of a clock travels how many radians in 15 minutes? So again, it might be helpful to think about a clock here. And so if we're starting right here and it's traveling 15 minutes, that's going to take it right over here to the 15-minute position. And so normally we would think of that in terms of degrees, and most of you guys would recognize, okay, well that it would be 90 degrees. And so if we want to write that in radians, if we want to write that in radians here, we're going to go ahead and take that 90 degrees. For that angle, we're going to multiply it by pi over 180. And when we do that, we end up getting 1/2 pi, or in other words, pi over 2. Next question here, the minute hand of a clock travels how many radians in 10 minutes? All right, so again, if we think about it here, 10 minutes is going to take us to about right here. And so I might have to do a little bit more thinking. But if we're thinking about kind of 5-minute increments, here would be 5 minutes, here's 10 minutes. Right here would be 15 minutes. So here's 15, here's 10, here's 5. And so if I know, and this would be like 0, right? And so if it's going to 10, it's going kind of 2/3 of the way to that 15 minutes. So I'm going kind of 2/3 of my way to that 90 degrees. And so if I'm kind of breaking it into thirds, that'd be 30 degrees each section. So this is going to be a total of 60 degrees because it's kind of covering 2 sections. And so if I'm wanting to convert that then, I would take that 60 degrees and multiply it by my conversion factor here of pi over 180 degrees. And when I do a little bit of simplifying here, I'm going to get pi over 3. Last one here, the minute hand of a clock travels how many radians in 5 minutes? So I should be able to use that diagram that I just drew here. 5 minutes is really just going to be kind of that first little section. So I know 5 minutes is going to be about right there, and so that's going to be one kind of 30-degree chunk there. So I'd be taking those 30 degrees, multiplying by my conversion factor, and getting pi over 6. All right, last one, a couple here. What is the measure in measure of theta in radians if x is 45 degrees? And so looking at the picture here, it's always good with geometry to label our given information. So we're given here that x equals 45 degrees. And so I am trying to do this in radians. So I'm going to go ahead and convert that here. So 45 degrees, I think we've already done that one before. 45 degrees when we convert here becomes pi over 4. And again, if you're not sure, you could do that conversion again. And so I'm trying to figure out the measure of theta in radians. And so I know that if x is 45, to get theta, I'm going to have to take the full 360 and subtract that 45, which tells me that my theta is actually 315 degrees. And again, I really want that in radians here, so I could go ahead and convert and multiply by my conversion factor here of pi over 180. And when I do that, I end up getting 7 pi over 4. Another option to figure that out would be to kind of use the fact that 45 degrees is pi over 4. So I could think of theta as being the full revolution being 2 pi instead of 360 and subtracting that pi over 4. And so if I think of it that way, I would need to get kind of common denominators here. So 2 pi would be the same thing as 8 pi over 4, and I'm subtracting a pi over 4, and that also would get me to that same answer. 8 pi minus 1 pi would give me 7 pi over 4. So another way to get the answer there. So looking at number 6, what is the measure of theta in radians? So kind of a similar question here. This time looking at the given information, I can see that theta is equivalent to 5x. and then its reference angle over here on this side is x. And so somehow I need to pull in some kind of measure here, angle measure that I can use. And so I see that I have a straight line. I know that that is going to be 180 degrees, or another way of thinking of it would be pi if I'm thinking in terms of radians. So I know that this whole angle here is 180 degrees, which is the same thing as half of that 2 pi circle, which would just be pi. So again, I can do this problem in degrees and convert to radians, or I could do with radians at the beginning. Either way, I know that that 180 degrees is going to be made up of that x angle plus the 5x angle, or in other words, 180 degrees is going to be equal to 6x. So solving that there, dividing by 6, I can figure out that each x is worth 30 degrees. So if I'm wanting to figure out what theta is, I know that since x is 30 here, theta is equal to 5x, which is equal to 5 times each x value of 30 degrees, or 150 degrees. And since I've asked for that measure in radians, I would then have to convert. So I would need to multiply this by my pi over 180. And in doing so, I would end up with 5 pi over 6. I could also do this problem using radian measures from the get-go. So another way to think about it is instead of thinking of that kind of straight angle as being 180, I can think of that straight angle as being pi. So I know that pi would have to equal x plus 5x, or in other words, pi would have to equal 6x. And so if I divide by 6, I see that pi over 6 is what each x is worth. And so then I could take that and plug it in and figure out what theta is. So theta would be equal to 5 of those x's, so 5 of those pi's over 6, which is just 5 pi over 6. And so I get the same answer doing it that way as well. All right, so your homework is the 4.1 homework worksheet. If you have access to a printer at home, feel free to print it off. If not, just look at the problems on the worksheet and just get out a piece of scrap paper, and you can write out the problems on the scrap paper. Try to keep it organized, label them here, and show all of your work there, and then that will count as having completed the assignment. So when I check for completion in class on Thursday, you can just pull out that scrap piece of paper that you wrote it on, and I'll check your work there. Again, if you happen to have access to a printer, feel free to print it and do it that way as well. Or if you have some kind of stylus pen and are able to write interactively, that's fine too. But a piece of paper and just kind of writing out the problems by hand will definitely be sufficient. So yeah, if you have any questions, feel free to ask me here, and I will be available by email all day.